This lesson is on rational graphs, and for this course, all we need to know about are two changes in our graphs. One is holes, otherwise known as points of discontinuity. So if you're reading a question, the mathematical term is going to be points of discontinuity. And the other item is going to be vertical asymptotes. So, as we get started, holes and points of discontinuity are literally what they sound like. Again, this is just like the math terminology, but the graph is going along, there's a hole in it, and then it keeps going along. So, when I say hole, that is what I mean. The thing about it is, we have to be able to look at the equation and tell that that's happening, because it is not going to show up on a calculator graph or on Desmos, because the technology likes to connect the lines, and so you're not going to see this popping up. Now, what happens is you can still know using a calculator or Desmos that there's one there, but you have to kind of know where to look. So if I click on the point on Desmos, it will show up as undefined. If I'm in the TI calculator and I hit on the table, it'll show up at that point as undefined. But I have to know to look for it and where to look. So it's important that we learn how to look at an equation and determine where that is. So we're first going to look at the steps that we take in finding a hole. And the first step, just like everything else we've done in this unit, is to factor. So it can be all kinds of factoring. GCF, difference of perfect squares, trinomials, anything can happen here. But you always start by factoring. And then we're going to look for something to cancel out. We're not actually going to cancel it out, and a lot of times I'll cancel it with a highlighter because it's still there. It's still part of the equation, but I'm thinking about that piece. Okay, I'm focusing in on it. What you're going to do once you determine that there's something to cancel out is you're going to find what makes that piece 0. Okay, we're going to find what makes that piece 0. In other words, what can I plug in for x and turn that into a 0? All right, so we're going to look at our first example here. And is there something that we want to cancel out? Yeah, so when we look at this, the x minus 1s are something that we would want to cancel out. So let me just highlight those for a second, okay? Now focus in on that. What could you plug in for x that would make that 0? So we would plug in 1. That means that there is a hole at x equals 1. So the graph's going to be going along. It's going to have a hole there, okay? Now, for today, we're not learning how to get the shapes of the graphs. We're learning about holes and vertical asymptotes. So we're going to let Desmos help us out in getting the shape of the graph, and we're going to sketch that down here. Now, I know that I'm going to have a hole at 1, so I'm going to mark that because that's going to remind me to put a hole there wherever the graph is at that point. Okay, so I go to Desmos, and I want to put in the equation just as I saw it in our problem, and I look at what's happening. Now, if you'll notice, 1 is about right in here, and I can even zoom in on it. It looks solid, okay? There's a hole there. You just can't see it because technology likes to connect the dots. And if you can click on it, it takes some skill here. If you can click perfectly on it, I'm not having success. It will show up as undefined, okay? So it will tell you that it's undefined if you know where to look. But for right now, what we're going to focus on is getting the shape right because we want to sketch these things today. So I want to pay attention to what's happening. So I have a curve that's kind of down here, and you'll notice it's getting close to the x-axis on this side, and this side's getting close to the x-axis as well. And it looks like at about -3, it kind of splits, and this end goes up and this end goes down. We are going to learn about that, but for right now, we're just kind of going to get that groove going and sketch our graph. All right, so as we come back over here, I want to remember what that looked like. So somewhere over here, the graph split, and this side went down, and I was close to the x-axis here. And on this side, it was up, and then it got close to the x-axis. But remember, when I get to 1, I want to stop what I'm doing, put in a hole, and then continue on. And you may draw it and then erase and put your hole in. It's fine, just as long as you show that there's a hole there. But we want the general shape, and I know that they're not going to be perfect today. Okay, so now the second thing we're going to learn about is a vertical asymptote. And this is going to make our graph sketch a little bit more specific. A vertical asymptote is a vertical line, so up and down, that the graph approaches, but it doesn't cross. Okay, so it gets close to it, but it doesn't cross it. And that was that kind of split up here. So if you imagine there being this vertical line right in here, and I've drawn pretty terribly, but you get close to it on each side, but you don't cross it. Like I didn't draw very straight down here, okay? But it shouldn't. It shouldn't cross. But it is a vertical line, and it does make the graph do some weird things, all right? They don't have to, the sides don't have to be pointing in opposite directions. They could be pointing in the same direction, okay? But that's going to happen. All right. So let's learn how to identify those. Again, our first step is to factor. And let me go to a color. We want to factor first, and you may have already done this because you've already looked for holes. So you're good at that point. And then pay careful attention to this sentence. You want to look for what gives you a 0 in the denominator, so the bottom of the fraction, not the top. A lot of people get mixed up. Just looking at the bottom, that isn't already a whole. So if you've located it as a whole, it can't also be a vertical asymptote. It's one or the other. It cannot be both. Okay? So this sentence is probably one of the most overlooked ones as far as people look at part of it and not the other. So you're looking only in the denominator, and we're looking for things that are not already identified as a whole. So if we go back to our graph that we were just talking about, we knew that we wanted to cancel those out, and that told us that we had a whole at x equals 1, because that's what made that piece 0. Now you look for what is left on the bottom that would also give you something. And so I'm looking at the x plus 3. So that's what's left. I didn't cancel it out. It's on the bottom. What would I plug in for x to make that 0? -3, right? -3 plus 3 would be 0. That tells me I have a vertical asymptote at x equals -3. Now, it's important that you put x equals with your vertical asymptote, because that is how we write the equation of a vertical line. The whole, I just put it there as a location, like identifying it, okay? But you need to have it with the vertical asymptote for sure. Okay, so this is going to make the graph that we just drew a little better, a little more specific. I know I've got a hole at 1 that I'm going to put in. But I also know now at -3, I've got this vertical line that the graph is going to get, like, not touch. It kind of splits this graph. The way you draw it in your sketch for me is by putting a dotted line in. So we do a dotted line, and then I can put my curves in. I know this one kind of looked like this, and I know this one came down, put my hole in, and I've made the graph a little better than it was before, a little more specific. Okay, now I want you to think about all the possibilities for equations. Okay, we've done a lot of rational stuff in here. Do you always have something to cancel out? No. Okay, not in every fraction are you going to have something that cancels out. So that means that you're not always going to have a whole. Some graphs have them, some don't. Some have more than one. If you had more than one thing to cancel, you could have more than one whole. But you don't have to have them. Okay? And then with the vertical asymptote, it's what's left on the bottom after you've done that. Well, what if everything canceled out? Would you have a vertical asymptote? No. What if the bottom piece was not something that could equal 0? You wouldn't have a vertical asymptote. So the point is that you could have, with either of these, you could have none, you could have 1, you could have 2. It's a variety of things, okay? So anything goes with what's possible. And these graphs are going to have some different shapes and some weird-looking shapes. Don't get freaked out by it. All right, so let's go to a more specific example. All right, so example 1. All right, how do I factor this? So our denominator is a difference of perfect squares. That means that I can write the factored form as x plus 1 and x minus 1. And the top is staying 2x squared. And now you ask the question, is there something I can cancel out? So is there anything I can cancel out? You think about the x squared, but remember that addition and subtraction are a very strong bond. And so this x is added to this 1. That's a really strong bond. You can't separate the two of them. This one is subtracted a 1 or subtracting a 1. Can't separate the two of those. In order to cancel either one of the things on the bottom, you have to have an x plus 1 or an x minus 1 on top. It has to be exactly like that because of that strong bond. So even though they're x's, they're not ones that we're allowed to cancel. So no, I can't cancel anything out there. Since I can't cancel anything, that means I have no holes. And so when you're doing practice problems, I want you to tell me that. I want you to put none. Because if you just leave it blank, I'm questioning, do they know what they're talking about? Did they even think about holes? You know, I need to know that you know what you're doing. Okay? All right, think about vertical asymptotes. What could I plug into the bottom that would make it 0? If I plugged a negative 1 in here, I would have negative 1 plus 1, which would be 0. If I plugged a positive 1 in here, 1 minus 1 would be 0. So I have vertical asymptotes at x equals negative 1 and at x equals positive 1. Now, before I even know what this graph looks like, because I'm not to Desmos yet, I can put those in. I can label 1 and negative 1 and draw in my dotted vertical lines that is going to kind of separate and chunk up my graph. But I'm going to go to Desmos to figure this out. Now, when you go to Desmos, you can plug in the original or the factored form. However, I suggest plugging in the original because if you have not factored correctly, you'll be able to tell it because your lines won't be in the right places. So we're looking to have our lines at 1 and negative 1. If I plug in the original and they're somewhere else, I know I've factored wrong. Okay, so let's go check that out. Okay, so when I type into Desmos, I can see that my lines look like they're in the right places. If you want to check for sure, come down on another line and type it in. So those were the two asymptotes I got. If I plug them in, I see that I've got them in the right places. They fit what they're supposed to. I have factored correctly. But I also want to take into account what's going on in this graph. Now notice this one has curves and these two are going up, and it's getting flat here, but it's not down on the x-axis like that original one was, and that is something that you're going to learn in the next course. We're just not doing it right now. But we want to make sure we flatten out above the x-axis. This middle section kind of looks like a parabola, but we know it's kind of bounded by those asymptotes that it's not going to cross. But I can tell it's going through 0, 0. So I want to go back and sketch the best possible option that I can. So I come back, I'm going to kind of draw my curves in, making sure I'm above the x-axis. And then that middle piece I know is at 0, 0 and going down. So something like this is a good sketch, and you're showing me you know where the vertical asymptotes are. Okay, as we look at number 2, the first thing that we want to do is to factor. And since this is a trinomial, I'm going to, on the top, be trying to find what multiplies to get negative 2 and what adds to get 1. and that would be a positive 2 and a negative 1. So I'm going to say x plus 2 and x minus 1. Then on the bottom, I'm trying to multiply to get negative 6 and add to get negative 1. That'll be a negative 3 and a positive 2. So I have x minus 3 and x plus 2. So now I want to look for holes and for vertical asymptotes. So the first thing I do is figure out, is there something I want to cancel out? And yes, in this case, I want to cancel out the x plus 2's. So what would make that piece 0? A negative 2. That means I have a hole at x equals negative 2. Now for the vertical asymptotes, I want to look at what's left on the bottom only, so just this part, and decide what would make that 0. And that will be a positive 3. So my vertical asymptote would be at positive 3. Now, yes, there is meaning to this top x minus 1, but we're not dealing with that today. It's actually where this is going to cross the x-axis, and you'll see that in Desmos. I'll point that out. But we don't have to find that today, okay? That's going to be in your next course. So, as I get ready to do my sketch, I want to make sure I'm putting a mark at negative 2, so I remember to put a hole there. And I'm going to draw a vertical asymptote at 3, okay, to shape my graph. Now, when I go into Desmos, I'm going to go back and put in that original one so that I can make sure that stuff is in the right place. And it looks like my vertical asymptote would be at 3, and that's what I found, so that is correct. Now, I mentioned the 1 because, yes, it is crossing at 1, but I don't have a vertical asymptote there. Okay, that's where I'm crossing the x-axis. It's not showing the hole at negative 2, and if I could get it correct, it would say undefined, but I can't get there right now. But notice where the curves are. So I have a curve here, and it's leveling out above the x-axis, and this one over here is also coming up above the x-axis and leveling out, and then they're splitting down and up at the vertical asymptote. Okay, so when I go to draw it, I'm going to draw this one that's nice and smooth and leveling out above the x-axis. And then this one over here is going to be above the x-axis. It's going to have a hole at negative 2. It went through the x-axis at 1, and then it kind of went down on this side of the vertical asymptote. So that's a kind of sketch for this. Okay, for our last example, I wanted to do something that is a little bit weird. So let's start with our first step, which is to factor. So consider number 3, can it be factored? No. When you look at it, you do have a binomial on the bottom, and x squared and 1 are perfect squares, but there's a plus between them, and 3 is not a perfect square, so that takes that out. So this can't be factored. The next question is, can you cancel anything? No. Again, if you think about the x's, this down here is attached with a plus 1 to something, so I can't just go canceling the way that I would want to, so that's out. What that means is I'm going to write there are none. There are no holes, okay, to make sure that everyone understands. And then I'm left with the bottom, okay? So I'm focusing on the bottom. What would make the bottom 0? What could I plug in for x that would turn the bottom into 0? Okay, so there's 2 ways to think about this. The first way is one that I spoke of in a previous lesson where we were talking about domain restrictions, and I said if you can't see it, then take the bottom, or whatever you're trying to look at, and set it equal to 0, and solve. So here I would subtract 1, so I get 3x squared equals negative 1. Then I would divide by 3, and then to get an x squared by itself, I have to square root both sides. So x would be the square root of negative 1/3. Now, Math 3 students, what did we learn about negatives inside of square roots this year? You have an I. So there's other things that we can do to make that answer look better, but the important thing here is that you have an eye. Now, did I teach you how to graph eyes? No, it can be done, but they have a special axis, like a special plane that they get graphed on. Here, we're dealing on the real X and Y axis that are only about real numbers. And so since this is an imaginary number and it's in a whole separate category, I can't graph it over here. Okay? So that is one clue that there are no vertical asymptotes. The other is to think about plugging numbers in, which is the way that I wanted you to start. What happens to any number that you square? Not, well, sort of, but like if I have a negative number, okay, -1 times -1 is +1. Any negative number that I pick, when I square it, I'm doing a negative times a negative. It's becoming a positive. If I put in a positive number, I'm getting a positive number out. So if you think about this, 3 times a positive number, it's always going to be something positive. And if I add 1 to it, it's even more positive, right? So that can never equal 0. There's nothing I can plug in that's going to make that equal 0 if it's always some version of a positive number. Okay? That does mean that's the other way to look at it and tell that there are no vertical asymptotes. So what does this graph look like? If we don't have any holes or vertical asymptotes, let's go to Desmos. So if we look at this in Desmos, and I'll even zoom in a little bit, it's kind of a wave thing going on. It does pass through the origin. You could figure out the maximum and minimums using Desmos, but it's a funky graph. But you can tell there are no vertical asymptotes, and we've already decided that there are no holes. So we're just going to sketch this to the best of our ability. So I'm going to try to be close to the x-axis, do a little dip, go through the origin, come up and do a little heel, and then come back down close to the x-axis. And that'll be my sketch for something like that. Now, you're probably not going to come across many like this. I mean, they do exist. It happens. But since your goal in this course is to learn about holes and vertical asymptotes, you're probably going to see more questions that have holes and vertical asymptotes. Okay, the last thing that I want to mention has to do with those domain restrictions that we talked about in the last class. And they're going to be easier to find now that you can think about things as holes and vertical asymptotes. Your domain is going to be everything but your holes and vertical asymptotes. So if you look at this little example I have here, do we have any holes? No. Do we have any vertical asymptotes? Where are they? A -2 and a +3. So if this question we're asking what is the domain, I'm going to say it's everything but 3 and -2. Now the way I'm going to write that is with an R with 2 lines. It looks like this. It's going to come across. That says all real numbers. In other words, everything from -infinity to +infinity. Okay, all the real numbers we can think of. But, meaning I need to put a not equals -2 and +3. That's the shortest way to write it. There are other ways to write it that are longer and using like the inequalities that we've used in the past. But to me, this is the shortest way to do it, and you understand what's going on. As long as you understand that this double R means everything that's possible from -infinity to +infinity. Okay? One last thing I want to mention is we talked about how the factoring that you could use could be anything. It could be difference of perfect squares. It could be trinomials. It could be GCFs. If I were to factor something that looked like this, okay, if I were to factor something that looked like this, what would you want to cancel out? The x's, okay? If I am trying to cancel out the x's, I know I've got a hole. Where would the hole be? What would I plug into x to make that 0? 0. Like, people overthink that. So this would have a hole at x equals 0. Okay? Don't overthink something as simple as that, because it can happen. All right.